When we think about the Mesozoic era, what often comes to mind is the variety of reptiles that once dominated the lands, seas, and skies of the Jurassic and Cretaceous periods. But these animals were far from alone, and often overlooked are the myriad of other creatures that were doing just as weird things and setting their own evolutionary records. In case you didn't already know, the earliest period in this time frame, the Triassic, had a lot of really weird things going on. So many that this channel is going to be dedicated to exploring as many of them as possible in this series, Triassic, What the F? Now, don't worry, we'll get to plenty of those vertebrates soon enough. But for my first entry, I wanted to focus on some non-bony buddies that deserve way more attention than they've gotten so far. Meet Gigatitan, a three-species genus of big insects that lived during the mid to late Triassic period. How big, you ask? That big. Maybe. Gigatitan was a member of the aptly and coolly named Titanoptera. These guys are an early diverging branch of the order Orthoptera, a group whose most familiar modern representatives include crickets and grasshoppers, and their reproductive anatomy, which will be discussed later, suggests that they are most closely related to, if not within, the suborder Incifera. These are your true crickets, dune crickets, katydids, camel crickets, grigs, wettas, and Kalula monsters, among others. Titanopterans themselves are commonly thought to have first evolved back in the Permian, although newer research indicates that they might have had origins going back as far as the Carboniferous, which the more paleo-geekier among you may recognize as the time of giant arthropods like scorpions, dragonflies, and millipedes. But not this.
The arthropods are back.
Speaking of outdated paleo memes, wait, you might say, I thought all the giant bugs died out at the end of the Carboniferous because of the drop in oxygen levels. Well, while at least terrestrial arthropods since then haven't generally gotten quite as large as they did in the Carboniferous, there's still evidence that suggests that the widespread extinction of the biggest terrestrial species had less to do with oxygen levels. In fact, the Triassic actually had lower oxygen levels than today, and had been sharply declining during the Permian, while Titanopterans seem to have only grown in size over the course of their evolutionary history as they spread across Pangaea to achieve a range spanning from Central Asia to Australia. So that should speak to the fact that oxygen availability isn't the end-all be-all factor for having big bugs. Although Titanoptera as a whole was first named in 1885, the bulk of research into these insects' anatomy and ecology comes from work started in the late 1960s by Russian scientists like Alexander Grigorovich Sharov, who named and described Gigatitan itself in 1968. These descriptions were based on fossil remains found in the Triassic-aged Madigan Formation, which is located in the northern region of the Turkestan Mountains in southwestern Kyrgyzstan, and dates back to the Landian and/or Carnian ages, some 242 to 227 million years ago, though the exact age of the site hasn't been determined yet. During this time, the area was a temperate, humid environment along the southern shore of a large inland submontane lake that gradually fluctuated in size due to the surrounding tectonic activity. The ebb and flow changes in the shoreline resulted in regions along the coast of the lake being a mix of swampy and forested floodplains and deltas, crisscrossed with rivers and streams that drained into the lake from further upland. Although there are remains from a variety of fish, amphibians, reptiles, and synapsids, this site is dominated by insects, with some 15,000 or so fossils known from this formation. Among the largest of these was, of course, Gigatitan. As aforementioned and implied by the name, these guys were definitely big, at least by bug standards, but exactly how big is a bit up in the air and complicated by two main factors. Firstly, few if any complete fossils have been found, never mind photographed, of Gigatitan and other Titanopterans, so it's hard to pin down their actual body shape and proportions from species to species, and good linear dimensions are hard to ascertain. What we do have of their wings indicates wingspans of anywhere from 24 to 40 centimeters, with one fossil from Madigan suggesting an individual with an over 50 centimeter wingspan. However, the second issue comes from recent researchers like Dr. Olivier Bethaud of the French National Museum of Natural History, who advises caution for this wing in particular.
And the specimen there's something important, they have been deformed, tectonically deformed. and to a large extent. Like you imagine a wing, it's fossilized in the rock, but then the rock, because of tectonic movements or whatever, is still plastic to some extent, and then will be elongated.
Right.
So in this locality, you have huge wingspan because they were along the elongation axis of the rock, so then they're bigger than what they were. I tried to do retrodeformation on these wings. I mean, not specifically Titanoptera, but from this locality. And what I derived is that the elongation factor varies. So it's very difficult actually to reconstruct them, but it can go up to 1.5 elongation factor.
Oh.
So it's very serious. That means that the longest wing possibly is elongated 1.5 times. So that makes a very huge range of possibilities.
This would mean that this potentially huge individual could in truth only be as small as 37 centimeters across. Of course, this would still be a bug with a wingspan of over a foot long, so it's not a terrible potential downside. Despite their iffiness on reliable size info, these wings can still tell us a lot about the biology and evolutionary history of Gigatitan and other Titanopterans. Current understanding of exactly how these insects are related to each other and other orthopterans has been informed by wing venation patterns, which is the shape and arrangement of veins running through the wings. It was this research by Betheau that led to the current thinking of Titanoptera being a group within Orthoptera, as opposed to just being a stem group. These fossils also show that Titanopterans like Gigatitan were capable of stridulation, which is the act of making sounds by rubbing two body parts together. In this system, one spiky body part, termed the scraper, rubs against the speaker, which is another body part that has structures that amplify and disperse the sounds. Scrapers and speakers can be any combination of limbs, wings, or mouth parts, with a variety of structures evolving independently across different arthropod groups, even within Incifera. In Gigatitan and other Titanopterans, the large rectangular window-like structures on their wings appear to be very similar to the speakers seen in katydids and true crickets, implying that, like their living relatives, these insects were producing territorial or mating calls by rubbing their wings together. However, as no fossil has yet been found showing the scraper, which would be difficult to preserve since such scrapers are usually found on the underside of the top wing, we can't yet know this for sure. Regardless of their exact method, the size of Titanopterans would result in notably lower-pitched noises than their smaller relatives, and these sounds would be picked up by tympanic organs located on their front legs, both of which are notions that you may find both cool and slightly creepy. Because of their large size and our lack of clarity regarding their true body shapes and proportions, exactly how flight-capable Gigatitan and other Titanopterans were is unclear, although it's usually hypothesized that, like many of their modern large-winged relatives like lubber grasshoppers, flight is something that they were capable of, but not especially good at. In such a swampy, forested environment with waterlogged ground cover, Gigatitan was probably at least competently volant enough to move from tree to tree, especially since its hind limb morphology suggests that it was not much of a jumper. Further evidence of an arboreal lifestyle comes from its reproductive anatomy. Like modern Enciferans, whose name derives from the Latin term ensifer, meaning sword-bearer, female Titanopterans had long blade-like ovipositors on the end of their abdomens. These egg-laying structures were armed with sharp ridges used to cut into plant material like leaf stems and bark in order to safely deposit their eggs. This behavior is called endophytic oviposition, and traces of this activity have been documented in plant fossils from rocks dating as far back as the Carboniferous, although none of these cases have specifically been attributed to any particular insect taxa. Little is known about the growth of Titanopterans, though like all arthropods, they would have gone through at least a few different rounds of molting their exoskeletons before reaching adulthood. Large arthropods tend to grow more slowly than smaller-bodied species, so it's not unlikely that it could have taken Gigatitan notably longer than modern relatives to reach their full size. What we do know is that these little babies would have grown up to become some not-so-friendly bugs. Unlike most of their modern relatives, Titanopterans were seemingly obligate carnivores, with fossils of Gigatitan itself preserving a head armed with robust and sharp incisivore mandibles that would have been well suited to cutting into prey. On top of that, their long forelimbs were decked out with a row of sharp spikes. These features, in combination with large eyes and long and sensitive antennae, suggest that Gigatitan was not just carnivorous, but an active predator, lurking among tree branches and using its arms to grasp unfortunate prey and bring it back towards its mouthparts. If this looks and sounds familiar to you, welcome to the concept of convergent evolution, where two or more relatively unrelated groups of organisms evolve similar adaptations to fit into the same ecological niche. We'll be seeing a lot of this throughout the series. These adaptations would have made Gigatitan one of the baddest bugs on the block, hunting the variety of other insects and arthropods it shared its environment with. Plus, if modern mantid and other predatory arthropod behavior is at all applicable here, it wouldn't be out of the question for the largest of Titanopterans to have preyed on some relatively large animals themselves, which, in the Madigan Formation, would put a menagerie of eclectic, small lizard-like reptiles on Gigatitan's menu, as well as some other potentially surprising quarries in other parts of Titanopteran's range. On top of this, their arboreal lifestyle and the seeming lack of comparably large carnivorous terrestrial vertebrates in their environments suggests that at least adult Gigatitans would have had little to fear, making these insects top predators. It's not clear why Gigatitan and other contemporary relatives in places like Australia went extinct by the end of the Triassic, especially after having survived the Great Dying, the biggest mass extinction event in Earth's history that wiped out an estimated 95% of animal life at the end of the Permian. Like their giant arthropod brethren of the Carboniferous, it likely had to do with a combination of environmental changes that they couldn't adapt fast enough to, and ecological competition from those pesky bone-having reptiles and synapsids that were taking over the land, and in the Triassic, the sky as well. Whatever the reason, the extinction of the Titanopterans marked the true end of the reign of the giant bugs, leaving us with mere clues of a strange world of foot-long cricket mantis chimeras, their deep chirps forever silenced. Comes from work started in the late 1960s by Russian scientists who named and described Gigatitan. Although Titanoptera as a whole was first named in 1885, the bulk of research